Welcome everyone to our C2M2 CPS speaker series. We are very glad to have Dr. Zadid Khan be our speaker today. So brief bio about Dr. Zadid Khan. So he's a senior data analyst in the supply chain department at Walmart, focusing on transportation. He received his PhD and MSc in civil engineering, transportation from Clemson University, and BSc degree in electrical engineering from Bangladesh University of Engineering and Technology. His primary research focus is cybersecurity and reliability of transportation cyber physical systems and connected and automated vehicles. Within the TCPS or transportation cyber physical systems and CAV domain, connected and autonomous vehicle domain, his research interests lie in data science, machine learning, deep learning, computer networking, data analytics, cloud computing, and optimization. During his PhD and MSc, Dr. Khan worked under the supervision of Dr. Ronnie Chaudhary on multiple projects supported by the Center for Connected Multimodal Mobility, or C2M2. It's my great pleasure to welcome Dr. Zadid Khan today.
Thank you, Dr. Chaudhary. Good afternoon, everyone. So can everyone hear me clearly?
Yes, yeah, we can hear you.
Yes.
Okay, so I'll just go ahead and start sharing my screen. Host disabled. So it says host disabled participant screen sharing. So if you could enable screen sharing, the host.
Hinkle, can you enable sharing?
Okay, thank you. I think I can share my screen now. So just to check if everyone can see my screen.
Yes, we can see it.
Okay, thank you, sir. Okay, good afternoon, everyone. So thank you, C2M2, for inviting me to give a talk on my research work that I have done during my PhD. So I'll just go ahead and start. So the title of my presentation today is Cybersecurity of Connected Automated Vehicles in Transportation Cyber Physical System with Artificial Intelligence. So just a brief overview of the transportation cyber physical systems. It contains many different components. It includes the connected vehicles, automated vehicles, and traditional vehicles also. And there is communication with many different infrastructures, such as traffic management center, traffic signals, roadside units. And then we have the cyber space with the cloud computing and the analytics that supports this physical infrastructure. And then there are some other services, backend services running. So the reason for giving this overview is that obviously I focused on a few specific areas of this overall transportation CPS domain. Today I will present two of my research projects. One is cybersecurity of in-vehicle network, and the other is cybersecurity of AI for autonomous vehicles. So today's presentation is more focused on the cybersecurity aspect of the transportation cyber physical systems. So first, I will present one of my projects on the cybersecurity of in-vehicle network. And the project that we worked on, I worked on during my PhD, is developing a long short-term memory neural network-based attack detection model for in-vehicle network security. And I will go into the details later. First, I will introduce how this project came about. So first, the motivation of the project. So in-vehicle networks are known mostly as the CAN bus, which is the most popular in-vehicle network, but there are also other types of networks. So these in-vehicle networks, due to the connectivity with the outside world of the connected vehicles, these in-vehicle networks can be attacked remotely and the network data can be altered to affect vehicle safety. So basically, this poses a major threat for future connected and automated vehicle technologies, a cybersecurity issue. So the motivation of the project is that the data-driven models can be used to detect anomalies in the in-vehicle network data and mitigate the effect of this attack on the in-vehicle network. So the contribution of the project were threefold. First, we created two types of attack models for this remote attack on the in-vehicle network. One is the reply attack and the other is the amplitude shift attack. And second is, after creating the attack model, we also created the attack dataset from attack-free canvas dataset. So we took attack-free datasets and we applied the attack on the dataset and created the attack datasets. And third is, we developed an LSTM neural network model for detecting the aforementioned attacks, which are reply attack and amplitude shift attack within the in-vehicle network. So this is the overall system diagram of the how the in-vehicle anomaly detection system will work. So here we have the CAN bus, which is a kind of a bus network that connects all the different ECUs, electronic control units. Here we have some example ECUs connected to the CAN bus, EMS, ABS, and MDPS. And then we have this malicious ECU. For example, it can be an OBD2 ports. How is this malicious? Because this ECU can be accessed locally or remotely by the attacker. So the attacker can inject data through this ECU. But how will the attack detection model work? So let's say we have this module connected to the CAN bus, and it can actually listen to the CAN bus data and process the CAN data and then input it to the LSTM model. And then the LSTM model outputs whether there has been an attack on the CAN bus. And since this is a model created by humans, we will have this model continuously being updated by verified users. So that's how the overall system works. Now, the first thing that we had to deal with is the data set creation process. So Canvas data is very low level, which means that it's in this type of formats, which is it has the ID, the DLC, and the data. These are actually hex use. So and then there's the timestamp. So how can you? So these are like very raw data that cannot be processed or used by data-driven models or machine learning models. So how can we process this data? So at first we need to actually decode the data. That is to understand what this data actually looks like. So, so here we have the raw CAN data, and then we have this message ID, which is in hex format. So we convert that to decimal, and then we have this file called the DBC file. This is used for decoding the raw CAN data. So here you can see that the ID actually corresponds to this number, which is the message ID. And then if the message ID matches, then actually we can convert these data to these different attributes. For example, these numbers actually don't make any sense, but these attributes make sense. So SAS angle, which is SAS speed, these are representative of characteristics of the sensors or data from the sensors, such as what is the current angle of the steering wheel, what is the current speed, and so on and so forth. And here is the ECU name, and these are basically parameters used for converting from this value to an actual value of the sensor signal. So these are all basically different sensors that are installed in the vehicle sends signals, and the ECU basically processes those signals, and it gets those attribute values from that. Now we work with two datasets. Dataset one was a raw canvas data collected by the Hacking and Countermeasure Research Lab. They collected it from the Kia Soul vehicle, from a real vehicle. And after post-processing the data, we extracted these 13 features from the dataset with these value ranges. For dataset one. Dataset two was a processed canvas data collected from the AEGIS big data repository that is also collected from real vehicles driven around in Europe. This dataset already had the 19 features because it's a processed data. We did not get the raw data for this one. So after the dataset collection, like attack-free dataset, we started working on the attack model. So first attack is the replay attack. Basically, it simulates the scenario when ECU is compromised by malware injection. It sends some previously stored data instead of current data. So this is replaying data from past timestamps, which are actually valid data, but this data is not valid in the current context. Basically, of the ECU functionality. So that's the first attack. The second attack is amplitude shift attack. Basically, when an ECU is compromised by malware injection, basically it can alter the bits in the data frame. And if you alter the bits, then the value of the feature will be shifted. Value of the signal will be shifted. So basically, amplitude of a feature changes, the trend of the variations over time remains unchanged because it is being shifted by a constant value. And in terms of like visualizing how the attacks look like, these are just examples on a few signals. One is the torque frequency signal and one is the engine speed signal. And this one is the replay attack. So here, I'll just show with this one. So in the first part, we see that the values are the same. And this x-axis is timestamp. So we are just checking by time. And this last part, the values are also the same, but in the middle part, the values are different. The blue one is the attack-free data. And the red one is actually data from a past timestamp that was saved. It is just replaying that data right now. So it is valid data, but not in the context of this timestamp. And amplitude shift attack, as you can see in this middle part, the amplitude has been shifted up because the bits in the data fields have been changed. So it has been shifted up. Attack data set. So this is just a summary. I won't go into too much details. It's just how we created. So we have basically 4 attack data sets, 2 from dataset 1, 2 from dataset 2 with different features here. So this is the attack detection model we created. So we have 512 LSTM neurons and then 8 fully connected, and then 1 output layer that gives us the attack or non-attack binary output. These are the model parameters from hyperparameter tuning that we achieved. So in terms of performance evaluation, we compared it with other data-driven models, such as MLP, SVM, XGBoost, KNN, RF, and NIPE-based. And for different, for the 4 cases, 2 for replay and 2 for amplitude attack, we see that LSTM performs better than the other baseline models across the board. One thing to note is that here we are presenting accuracy, precision, recall. Because for attack detection scenarios, precision and recall are very important because it focuses on the correct attack predictions. Precision is the percentage of correct attack prediction out of all attack predictions. So in that scenario, the models are doing well, and even LSTM is doing the best. It has relatively good precision for all scenarios. But for recall, there is actually scope for improvement. because the percentage of correct attack predictions from all attack instances. So let's say there were 10 attacks, and basically how many attacks the models were able to develop. So for amplitude shift attack, LSTM does very well. But for the replay attack, there is actually scope for improvement in that scenario. So further research can be done in this case actually. Okay, so I will go ahead and start the second research project. If you have any questions, actually, you can probably ask about both projects at the end, if that's okay with everyone. So that was the first project. We looked at the cybersecurity of the in-vehicle network. Now, another important part of the vehicle is basically the internal control, perception, and control mechanism for autonomous vehicles. It's basically all software based. There are many instances where AI models are used. For example, for perception module, AI for like computer vision, and these type of things, AI models are used. Now, the security of AI is a very important topic that needs to be addressed in research. So our project is we developed a hybrid defense method against adversarial attacks on traffic sign classifiers in autonomous vehicle. Traffic sign classifier is a part of the perception module in the autonomous vehicle, tries to identify what type of traffic sign is currently in front and act accordingly. So motivation. So what is the background? So adversarial attack. First of all, what is adversarial attack? It is basically attacking the system AI model in the in-vehicle network. How it does that is basically it introduces some noise and perturbations in the images, so that the AI model basically misclassifies the image. And here we can see that actually, in effect, this is actually from one of our demos in 2019. If you are around, you are actually part of this. We created this, showed this in a vehicle that the actual sign is the traffic stop sign that we actually had in front of the vehicle. And we had this NVIDIA TX2 and this camera, and it was processing the camera image and classifying as a stop sign. But then we introduced the adversarial attack, and we actually showed that it was misclassifying it as a 45 mile per hour sign, which is very dangerous, because if the vehicle acts accordingly, it will cause crashes. So this is basically the motivation. So what is the contribution? We developed a DNN-based hybrid adversarial defense approach for traffic sign classifiers. It incorporates the following techniques: random filtering, ensembling, and local feature mapping. Basically, the defense method achieves similar accuracies in attack and non-attack scenarios, and it is irrespective of the type of adversarial attack, which are very important things. We want the model to perform well in non-attack scenarios, obviously, but also when there is no attack, the model should have good performance, and also it should be irrespective of the type of adversarial attack. So it should be applicable to all types of scenarios, because different types of new attacks can be created in the future. So again, this is just an overall representation, high level of how it's working. So we have we have an image of a traffic signal, for example, stop sign. The attacker introduces a noise, and then basically it goes through the neural network, and the neural network is supposed to classify it as a stop sign, but it's doing the wrong thing because the noise has been introduced in the image, and the neural network has been trained on correct images, not noisy images. But here, how the defense method is working. So at first, we may have some filtering techniques, and then we have some verification models that actually corrects the model. Although the neural network model might be trained on clean images, these filtering techniques and verification models will correct the classification of the okay. Again, of course, we need that data set. So we worked with the Lisa traffic sign data set, which is a set of videos and annotated frames containing US traffic signs from different cameras. So here, basically, the cars were driven around, and you see these annotations and bounding boxes, basically, with the traffic signs. It contained 47 US sign types and 7,855 annotations. Video frames varied from 640, 480 to 1024, 522, and the annotation frames varied a lot. It can be 6 by 6, very small, or it can be 167 by 168. That's the range. And it contains different types of metadata. Obviously, this data set is not suitable for, because we're doing traffic sign classification. This data set is not currently, in this format, it is not suitable for classification. So we had to convert it to a classification data set, which contains different types of traffic signs. So after looking at the number of instances or number of images for each of the traffic signs, these are the 18 traffic signs that had sufficient data such that we can use it for a traffic sign classification model. So these are the most common traffic signs that are used in the US, and this had sufficient data. So we created this data set with 18 traffic signs. And then the attack model. So we adversarial attacks are already have been researched thoroughly, and like every time, like different new attacks are being proposed. So at the time we did the research, we searched literature and found the state-of-the-art adversarial attack models, which are showing the most good results in terms of like misclassification. So these are the attacks at that time that were doing the most highest number of misclassifications. And basically we tested the data set with how this attack works. And here is just an example. If we attack using the FGSM, I would go to the attack models too much because that's a different conversation. So these are the misclassified labels that you can see. All of the cases we have misclassification. None of these are stop sign labels. So it's, in these cases, it's merge, and the last one is do not enter. And the model that here the model that we're showing as the classification is the Inception V3 model, which is a very well-known model for image classification. It has shown one of the best results in the benchmarking tests, such as dataset from CocoNet and Coco dataset and ImageNet dataset. So this is again just showing the steps of how our hybrid defense method actually works. Initially, the first step is identify initial labels using the retrained Inception V3 models and craft CRN model. And this is called low-car feature mapping. So I will go into the details of that, how that works. And we check if the label is matched or not. If it's matched, then obviously that's the correct prediction. If it's not, then we need to identify the candidate labels from Inception V3 and ResNet 152, and then use an ensemble technique. Here we have used plurality voting to find the final level and then start. Now, there are two phases of the defense method. One is obviously the training phase. At first, we train, because we're using both Inception V3 and ResNet 152 and doing some ensembling, we need to actually train the models first. So for Inception V3, and they're both trained on the Lisa dataset. For Inception version 3, the input is 299 by 299 by 3. So obviously, Inception v3 is initialized with pre-trained weights. That is generic. It's basically generic to all types of image classification. But then we add these additional layers at the end, 2048 and 18. And we get the 18 output labels that we need for the 18 traffic signs that we have. For ResNet, there is a conversion step, which is we need to convert these 299 by 299 by 3 images to 224 by 224 by 3. Because that is the input dimension to the ResNet 152, and the rest of the process the same. It gets this output, and basically this whole training process happens on clean images. There is no adversarial attack happening here. Yeah, so that's the assumption that the model has been trained on clean images, so it will have difficulty identifying when there has been an adversarial attack. Now, this is the important part, which is the testing phase, where we actually have the adversarial attack in effect. So how will our system respond to that? So again, we have this input traffic sign. It can be regular or adversarial. And it goes into two models. First is the Inception v3 model. And the attack, there has been a white box attack on the Inception v3 model. So the previous attacks that we showed, those are all white box models. So they have actually knowledge about the Inception model itself. So they can actually use that model to create better attack models. So actually the attack, since it's based on this, most likely scenario is that this model will actually misclassify it. But how are we taking care of it? So first is the part, the blue part, as you can see, is the local feature mapping part. So what is local feature mapping? So the graph plus CRN model is also a pre-trained model, but what it does is it basically identifies texts in images and basically creates bounding boxes for those. So the output of this model is word and region. So region is basically the bounding box where the text is in the image, and the word is what is the word in the image. So identifying the actual text. And then we have this word template matching, where we have a template for traffic signs. So some traffic signs will have some text, some traffic signs will not, but we have this template that matches these words. And then after matching it, basically, if there are some text in the images and the text matches the template, basically we can extract a traffic sign level from that. So this is actually the first step where we're actually trying to counteract the attack by looking at a local feature rather than the whole image itself. So from here, we try to find a match. If it is a match, then we say that, okay, this is the sign level. If it is not, then we move on to the next part, which is here you can see the color. It's doing random filtering. And the random filtering, the purpose of random filtering is basically introducing randomness. So it is the most popular method for counteracting an attack. It introduces randomness in the classification process such that the attacker is actually not able to deterministically create an attack model for that. So here we're doing that. How we're doing that is we're doing random cropping, which is we're going from 299 to 280, but we're doing it randomly. So this frame within this whole image is taken randomly. So that introduces the randomness in the process. And then we actually resize that to a 299 by 299.3. The advantage is that obviously we're introducing the randomness. The disadvantage is we are actually losing a partial part of the images but previous research has shown that image classification models are able to classify images correctly, even with partial images, not the full image. So, and then after resizing, we actually can run this multiple times. So if we run this process m times, we will get m samples. And if we run this process n times, we get n samples. And each of the samples can be input to the deep learning model, Inception or ResNet. And then if we have m samples, we get m labels. We have n samples, we get n labels. And then we basically have m plus n labels. And we need to identify a process to actually find out what the actual level is, or the actual output is. And we use this ensembling technique called the plurality voting, which is basically looking at what is the majority of the output is. And based on that, we determine what the traffic sign level is. So performance evaluation and benchmarking. First thing is we need to make sure that it has the difference method. So if I go back, so this is, instead of just directly getting the traffic sign level from this model, Inception 50, we're introducing this whole difference method, but this difference method is not dependent on any detection of the attack, right? So it will always be active. So we need to make sure first that in no attack scenarios, the model performs well. So the first row is actually the baseline. So basically using transfer learning, we have shown that the Inception V3 model by itself in a no attack scenario can predict the correct class traffic sign level with 98% accuracy with a good precision recall and inference scope. And hybrid model actually performs better. So it actually slightly improves over the Inception model in the baseline scenario. So now we can actually explore the attack scenarios because we have made sure that it does well in no attack scenarios. FGSM attack and MIM attack. So here you can see, I will just highlight the accuracy, 89%, and overall we can see that it has higher precision and higher recall than the other models. And also for MIM attack, it has similar numbers. The recall is a little bit lower here, but it is higher than all the other models. So the important thing to note is the what is the strength of the attack. So as you can see, FGSM attack is not that powerful. Even with the attack, the accuracy is actually 75%. But MIM attack is a very powerful attack. If you actually use this attack, your baseline accuracy for the Inception model actually goes down to 10%. So only 1 in 10 traffic sign levels are classified correctly, which is a very low number. And our defense method can take this up to 87%, which is relatively good compared to the baseline. PGD attack and CNW, we have similar results. These are also very powerful attacks. For PGD, we can see the accuracy is 8%. But the defense method accuracy is actually 87%. And for CNW, it's slightly higher, 13%, and then it's 89%. So across the board for different types of attacks, adversarial attacks, we are able to show that our defense method outperforms other baseline methods. Now, one important factor about the attacks, without going into the details of the attack models, is epsilon. So epsilon is a value that signifies the magnitude of the noise or the perturbation introduced. So if I go back a little bit. So here we can see these attacks. These are the clean images. So adversarial image, apparently, to the human eye, it's actually not changing too much, but the perturbations introduced in these images actually come from a solid like mathematical background, and basically these are images that are designed specifically to fool the Inception V3 model into misclassifying. So that's kind of the background, and there are some noises and perturbations in these images. So the magnitude of that is actually measured using CPS, which is the epsilon, and a typical value that we used to generate these results were 0.1. But we then try to understand that, okay, what is the effect of this value? If we vary this value, how will it affect our model, or in fact the other model? So here you can see, so epsilon 0.05 means a very low perturbation. So here, obviously, you can see the accuracies are kind of clustered towards the top for all three attacks. The minimum is above 70% here, it's around 40% here. But going down to 0.1, here we see some the other models degrading, and similar things happening here. And if we go to 0.2, which is a relatively high value, which is actually 20% perturbation or noise, most of the models actually, for this one is close to 50%, and actually for these it's close to 0%. Actually the accuracy. So it totally misclassifies because of the high noise and perturbation in the image. But the orange here is the hybrid model, and it does degrade slightly. Obviously, as the noise or the perturbation increases in the image, every model will perform poorly, but it tries to maintain relatively good an accuracy. Now, we kind of looked at the overall results. So this is class-wise performance for the for a specific case. I think this is the PGT attack. So this is the result for the PGT attack with epsilon 0.1. Now, again, just to show this is showing the precision recall F1 score and the number of samples. So different number of samples, that's one of the reasons for the different results. For a few traffic signs, it performs, it has some issues. One is do not enter. As you can see, it has a very low precision, and pedestrian crossing, so low precision, and also the recall is a little bit low for roundabout. As you can see, the speed limit signs are, the performance is very well. And for these other signs, curve left, curve right, and lane ends, merge, these are performing really well. So then we actually tried to develop this, which is kind of the confusion matrix. The left is the actual class, and the top is the predicted class. So here we can actually see what the reason is to actually kind of identify. For example, if we go back, we can see a pedestrian crossing, for example. So it has a precision issue. So here, if we see the pedestrian crossing, is that the issue is on the column side, not the row side. So here it's showing that it's over predicting the pedestrian crossing. So the actual is 74, but here we see that it's a curve right sign, but it's predicting as a pedestrian crossing sign. So it's predicting different other signs as pedestrian crossing signs. So these are the type of things that we need to kind of look into and try to improve these numbers, basically. So here we are at, let's say for PGT attack, we're at 87% accuracy. So in order to actually improve this, we need to go into the class-wise analysis and then try to identify why for this particular traffic sign, it is not doing well, and then try to maybe improve the model, do some sensitivity analysis, and improve the overall performance of the model. So that's all I have for today. Thank you for joining this session. And if you have any questions, I would happily answer them. Thank you.
So Dr. Khan, I will start the question, and please, audience, if you have any question, please write it in the chat box or just directly ask in the speaker. So I have a question. So in the last slide, so you were showing that the precisions, recall, they were different for different types of signs. Do you think it is related to the method, or just random, that if you have done more testing, it would be similar across all signs? Is this a characteristics of the sign, you think, or just randomly it happened? Is it something to do with the do not enter sign?
Right.
Yeah.
Right. So yes, thank you, sir. That's a valid point. So I think both are contributing here. So first is, if I go back, actually I can show it here. So first thing is, the samples are actually collected, the traffic sign samples, from video frames. And sometimes the annotation frames are large and sometimes they're small. So the quality of images for all traffic signs are not the same, and the number of samples are also not the same. So what happens is, maybe for pedestrian crossing signs, the sample quality was not that good. What that does is, basically, when we have some traffic signs with maybe not so good resolution or sample size, the introducing the noise and the perturbation degrades the quality of the image. So that may be contributing towards the lower precision here. Another is actually the model itself. For example, we are using the local feature mapping here, which is kind of focusing on the text part. So one reason that the speed limit signs usually are doing well is actually the speed limit signs are more text-based. So introducing perturbations for these types of signs, the local feature mapping is very strong and is actually able to extract the texts and the context from the images and is able to classify correctly. Whereas for maybe traffic signs that may not have texts in them, so they are only dependent on the random filtering and the ensembling. So the local feature mapping is actually not active there. So in that case, the performances may vary between traffic signs.
Right. So I'll say that what you said, that one could be just the way you use this LISA database, the way they are in the database, it might be contributing to this difference in the precision recall.
Yes, sure, sir. Yes,
yeah,
definitely.
And the second point is because you're doing this text recognition, so that might be for the speed limit sign, is producing higher accuracy. So so if you are doing a paper, or so you just write those in the limitation section. Okay, so this is what happened because of the database that we use, but it might be different in the for the first limitation. The database, it will not be like that in the real world, right? So because you'll have every sign should be equally visible, hopefully. So it could be different. So that we should discuss then. And about this text recognition, so that could be a reality in the field, because you can more accurately predict if the sign has text. Yeah.
Yes.
Thank you. I think there is a question in the chat box.
Yes. So the following question is dataset pre-processing for the in-vehicle network attack using the HCR dataset, so that there are actually very small overlap on the decoded features for different issues connected to the canvas for your project. But the attacks focused on particular issue. Also, do you think it is possible to detail? Okay, I'll answer one by one. I think there are a few questions here. First question is, where the attacks focused on a particular issue. So the answer to that is actually no. It's actually not on the issue level. It's actually on the signal level. So it was not focused on one particular issue or signal. It was actually data from different sensors. So if I go back, where's that slide? Okay, so these are the data set. So here, so I showed this as an example. So this is how the data is, and here you can see that each data set has a timestamp, right? And here you can see that for this ID, because this ID represents this value, and then this is actually specific to MDPS. So here you see 0 to B0, we have 2 lines of data, but in between we have other data also, and it's not like we just use MDPS or this decoding. We had different DBC files, or the same DBC file had information of other issues also. So it's not like we only extracted this line and this line. We also decoded these lines also, and basically what we found is that there are these 13 features from that data set which were extracted from correlation analysis. So we did a correlation analysis and found that these features have correlation among each other. And these are, as you can see, these are TQI, means total quality indicator, break, this is TPS, and these are all from different sensors that are set up in the car, and these values are basically extracted from that. So that's I hope that answers your first question. The second one is project attacks focus on particular ECU. Also, do you think it is possible to detect an attack better perform for replaying multiple issues without having multiple models? Okay, so this next question is more specific, I think, to the replay attack. So it's saying that for replay attack, so can we have only one model to detect the different types of attacks, or do we need multiple models? That's obviously multiple models for different types of attacks will obviously perform better. So that's the first thing. If we train a model for a specific type of attack, let's say replay attack, and train a model, so that will model is specifically tuned to detect that specific type of attack, so it will perform better, but it will add a lot of computational load, and if the computation is supposed to be handled like very efficiently, then it might be suitable for like a real scenario where the vehicle will have one model for multiple types of attacks. Because these are all anomalies. So basically we're trying to detect anomalies in the data, and there might be different types of anomalies in the data set, but a model with that is trained with sufficient amount of data or anomaly cases should be able to detect future anomalies also. So I would suggest not one model per attack. It might be one model for few attacks. If that makes sense.
Yes, and I agree with Dr. Khan that the most efficient would be if you have one model that can detect multiple attacks. Otherwise, it may not be practical in many applications. So, yeah, you always try to develop a model that can detect multiple different types of attacks. And also, one more thing I would also say that if you can have, you may not know whatever attacks will happen in the future. Right. So if you can have some type of adaptive security, like adaptive detection based on what may come in the future, it can adapt to it. That would be ideal. Yeah. Yes. So we call it adaptive cybersecurity. Thank
you. Any other questions?
Yes, I have questions about your second project, the adversarial project. So I think you were proposing a hybrid ensemble defenses for the adversarial attacks, and I think it combines 3 different techniques.
Yes.
So have you evaluated the overall inference time of your defenses? Because I think there were 3 neural network inference processes, right? So I don't know if, because this is for the traffic sign classification and it has to be run in real time, I think.
Yes.
Yeah.
Yes.
Yes. Yeah, Zadid, the time. Yeah.
Thank you. Yeah, thank you for the question. Yeah, it's a very valid question. I don't have the results here, unfortunately, but I did compare the computation time, and when I say computation time, I'm talking about the testing.
Okay.
So I compared the computation time of the hybrid model with all these other models. Because of this overhead of the defense method, obviously it takes longer than these baseline models, but the difference is not significant. So
Okay.
the improvement that we're achieving is far superior compared to the increase in computation time on the testing phase.
And what kind of machine you are testing on? Is NVIDIA Jetson TX2 or?
These models for generating the results for the paper, all the models were run in the Palmetto cluster.
Okay.
In a real world scenario, obviously it will be run in a Jetson TX2 or a NVIDIA Xavier, I think is the new one.
Yeah. So do you think that one is powerful enough to, because Palmetto is pretty powerful, you know?
Yes.
Yeah. So compared with Jetson. So I don't know if Jetson is powerful enough to.
Yes, definitely. You know, that's a valid point. I think another test case can be developed where all the models are run in an embedded device like Jetson TX2, and the computation should be compared based on that.
Okay. I have another question. So
Yes.
you have the FGSM, the MIM, and PGD. Also another one I think is C2M2 attack, right? So have you ever noticed the difference between the attacks, like which one is stronger and which one is more difficult to be defended?
Yes.
Yes. So for this test case scenario that we have developed, from the results, actually you can see that the PGT attack is the most powerful. If I go back, so if you look at the no attack scenario for inception v3, the accuracy is 98%, and if you use a PGT attack with an epsilon value of 0.1, your accuracy drops to 8% from 98%. So that's a 90% decrease in accuracy. So PGT attack shows to be the most powerful attack model out of all the ones that I have used in this study.
Okay, and may I ask what kind of EPS you are using for this attack?
Sorry, can you repeat that?
The EPS, the epsilon.
EPS is 0.1.
0.1. Okay.
0.1. Okay. Yes, but we also did a sensitivity analysis.
0.1.
We are doing for
0.05,
0.1, and 0.2.
Okay, I see. Okay, thank you very much.
Thank you.
Thank you. Any more question from any audience member? So we are close. It's almost 3. So thank you so much, Dr. Zadid Khan. So we really appreciate you spending time with us and presenting your talk today. It was wonderful. We learned a lot. Thank you very much. Thank you, from C2M2.
Thank you. Thank you for inviting me. Thank you.